too many nodes in a neighborhood, and one node wants to talk to the others and just sends out in a flooding mode, broadcast in a flooding mode packets, and all the nodes repeat that, and then you overload the network. So another one is packet dropping, and the most malignant form of this attack is the one where colluding nodes attack your distributed denial against a specific, mount a distributed denial of service attack against a specific node and isolate it. How to deal with these things? Well, you can use various ways. One is intrusion detection techniques. If it's not malicious, there are nice ways of doing it using gossip protocols. These are protocols in which somehow reduce the redundancy in a clever way. If it's malicious, one way is to have denial of service, intrusion detection mechanisms. That doesn't work in general very well. A better one is to have fault tracing mechanisms and some kind of redundancy. So if something doesn't come from one path, it comes from another path. I'll talk about this more. The man-in-the-middle attacks are sort of more nastier because what the enemy does is the enemy sort of takes control of the communication between two nodes by interposing between them. So the nodes are not neighbors, but the enemy somehow gets close to the one and sort of through some other one close to the other, so it sort of then relays packets from the one to the other. If it's a passive attack, then the enemy just relays packets, nothing else. And that may seem harmless, except that because the enemy has taken control of the communication, the enemy at any point in time, if the message is sort of critical, can halt it, can stop it, and that would be a denial of service. And it's a smart denial of service. It is only there when there is a good reason, when the enemy wants to stop it. So the enemy, by having control of a communication channel, can actually prevent certain things happening when they would do most harm, for example, to the enemy. The active ones are even worse. The enemy then puts on a face. He's an insider, a respectable node, a node with a public key. Everybody knows it, but it misbehaves. And there are three attacks which I won't have enough time to describe, but they're all rather clever, and they all have disastrous effects on communication. They come under sort of different names. One is called wormhole, the other is called rushing attack, and the final one is Sybil attack. The wormhole attack is an attack in which two malicious nodes, what they do, use their special covert channel to communicate, and the one links up with the one system and the other, and they actually pass all the messages through the one, and so the two nodes which communicate through this channel of the malicious nodes may think that the route is very short, because essentially it could appear to them that there are only three nodes, or four nodes two nodes between them, the two malicious nodes, and actually the distance may be much longer. So they may prefer to choose this route, the path from other paths, because it's the shortest. It appears to be the shortest, the most effective. Whereas it isn't, and it's under the control of the enemy. The rushing attack is a sort of twist of this. What happens is the malicious nodes can actually rush through the packets, through these covert channels, much faster than what happens in the normal network, and that gives them even more power. And the Sybil attack is the attack in which actually they share their secret keys, and a node can present itself to its neighbor as being 5 different nodes in 5 different faces, if there are 5 bad guys. How do you counter such attacks? Well, that's hard, and these are the hardest to counter. There are 2 out-of-system methods which are used. Sometimes these attacks cannot be solved, cannot be addressed within the system. And usually these are addressed out of the system. And the one is a temporal and the other is locational. The temporal deals with the time. speed of light is that's your upper bound. The time it'll take to rush through this sort of packet cannot go faster than the speed of light. If you have very accurate timing devices, maybe you could do it. The second has to do with the location. If your neighbor claims to be 5 different people, then you may insist on getting authenticated, signed copies of this sort of position. And then each one will sign that position. But at the same time, somewhere far away, another malicious node will do exactly the same. Now, if you have 2 signatures of the same node, which one's in place 1, another 15 hops away, then that node is a lying node. And that's how you can deal with it. The security is typically dealt with in a protocol in different layers of the protocol stack. And there is a reason why, and why it can be done, and how it can be done, and why it can't be done in a sort of an arbitrary way. And this has to do with the fact with the faults that occur. So you have 2 essentially types of faults. Faults that are whose effect is stochastically indistinguishable from ordinary link failures. So they occur independently with a certain predictability. You know them. And they're not dependent. And they are caused by the mobility of the system, radio interference, the sort of thing when bulbs sort of have a life expectancy and they won't last too long. And you can design methodologies to deal with it by having 3 bulbs instead of 1, and when 1 goes out, then you replace it. And there are the other kind of faults which are not stochastically indistinguishable from ordinary link failures. The first type can easily be addressed at the medium access control layer by using the standard sort of error correcting or sort of ways, and that is used, and it's quite. So if a packet gets dropped, it gets dropped with probability, say 2/3, then you ask for it to come back. Well, with a high chance it'll come back. If it's maybe the second time it doesn't come back, but then the probability that the third time is much smaller, so you can deal with this. The malicious ones certainly cannot be addressed at that layer. So anything which has to do with malicious faults must be addressed at the protocol layer. One last, so that you cannot assume that the things will be sorted out at a lower layer and you won't see them. Some faults will have to be addressed at the higher layer. And just a remark here is that one of the nastiest attacks that the enemy can do is to hide behind this differentiation. So the system at the medium access control layer deals with faults which occur with the sort of predictable probabilities. And the enemy can mask an attack pretending to and using this probability. So the system will try to, at the message, a medium access control layer, they will try to work it out, but this is much clever. Although it happens with a predictable probability, the probability, it's not independent. It's very dependent on what happened in the past. So if you try to just get a sort of, so the packet is dropped and you never ever get the packet again. So the system just works and runs and runs and runs. So that has to be addressed. As I pointed out at the beginning, there are a lot of good protocols which have been proposed in this area, and they're highly reliable. Some of them actually involve the people working at Purdue. They have been designed to be very efficient and very reliable. They were not intended to be in a sort of security framework, especially not with sort of the malicious type of attacks I'm talking about. And so it makes sense to try and, at this point in time, to find ways